Hi, my name's Justin. I'm a first year HIS student at Conestoga College, and today I'm going to be discussing the auditory system, mainly focusing on the middle ear, its structures, and how it contributes to hearing. So without further ado, let's take a closer look. So sound travels through the air as vibrations called sound waves. We're going to use this pipe cleaner as our representation of a sound wave. When these waves reach your ear, they enter your outer ear and travel down into your ear canal, where they eventually reach the middle ear system. Middle ear is home to several structures, primarily the eardrum, also known as the tympanic membrane, the eustachian tube, and the three smallest bones in the human body, known as the ossicles. Each of the ossicles have their own name. Here we have the malleus, the incus, and the stapes. Altogether, they form a chain which connects the eardrum to the inner ear. The inner ear contains the cochlea, the organ of hearing. It's not a part of the middle ear system, but I felt the need to include it since it gives us a better picture at the primary function of the middle ear. So we'll be referring back to that in a little bit. Returning back to sound waves, the wave travels along the inside of the ear canal and eventually makes contact with the eardrum, causing it to vibrate. I'm going to stop doing that because I might break it. Use your imagination. That's vibrating. So the vibration from the tympanic membrane moves on to the ossicular chain, the malleus, the incus, and the stapes, and eventually ends up on a little spot right here known as the stapes footplate. Stapes footplate presses up against a spot on the cochlea, known as the oval window, and this actually causes an amplification of the wave itself. So basically the sound wave will sound louder due to the increase in pressure from going from a much larger area on the eardrum to the smaller area of the oval window. So one of the primary functions of the middle ear system is the amplification of sound, making it sound louder. The other main function of the middle ear system is impedance matching. Sound waves typically travel through the medium of air, but they are also capable of moving through other materials and mediums as well. For example, the cochlea is filled with fluid, and as we know, fluids such as water are much more dense than compared to air. So this means that the sound wave will take a much longer time to travel through the fluid-filled cochlea as compared to the air-filled ear canal. Now, this difference in impedance results in the loss of approximately 30 to 35 decibels of sound energy. The auditory system wants the transfer of sound energy to be as efficient as possible. So the middle ear overcomes this issue through the use of three methods: condensation, lever action, and the buckling action of the tympanic membrane. Now, this is going to involve a little bit of math, so buckle up. So as I said before, the impedance loss when going from air to fluid is approximately 30 to 35 decibels. The first method of overcoming this loss is condensation. Condensation basically refers to the tympanic membrane, or the eardrum, being much larger when compared to the oval window. Like we said before, it's actually larger by a magnitude of 17 to 1. So this results in a 17 times increase in force. Second method is the lever action, which basically refers to the handle of the malleus being approximately 1.3 times longer than the long process of the incus. This results in 1.3 times increase in force. Finally, the buckling action of the tympanic membrane. So this basically refers to there being more movement and less force on the outer edge of the tympanic membrane when compared to the center. Center is where the umbo of the malleus actually connects to the tympanic membrane. So this leads there to be less movement, but more force on the umbo where the malleus is attached. This increase in force is approximately a 2 times increase in force. So the total increase is 17 times 1.3 times 2, which leads us to a ratio of 44 to 1. Great. Now we just got to convert that into decibels. So in order to do that, we are going to use this sound pressure formula right here. So 20 times log, and then our ratio here. So let's put that into the calculator real quick. So 20 and then log And then our ratio of 44:1, which gives us approximately 32.8. We're going to round that up to 33. So this is essentially overcoming our impedance loss. We lose a little bit in the upper edge there, but it's a range. So we're pretty much entirely getting over that impedance loss thanks to these three methods from the middle ear system. And that brings us to the last portion of the middle ear that I'm going to be discussing today, which is the eustachian tube. So the eustachian tube's main purpose is to equalize pressure on both sides of the tympanic membrane, as well as draining out fluids from the middle ear. These functions are very important as they allow the eardrum and the ossicles to vibrate more freely, as well as prevent them from being damaged. On our model here, the eustachian tube is opened, although in reality it is typically closed, only opening for actions such as swallowing, yawning, sneezing. All of these things will cause it to open up temporarily and allow that pressure change and the drainage of fluids.